Hi, in this video we are going to study the trigonometric form of the Fourier series. Now, first of all, let us remember what we mean by the Fourier series. X of t is a periodic function or signal with fundamental period capital T0, and x of t therefore has a Fourier series representation given in terms of the superposition of harmonically related complex exponential signals. So k from minus infinity to plus infinity, ak e to jk omega 0 t. Here omega 0 is related to the fundamental period by means of this expression. 2 pi over t0 is equal to omega 0. So this is the form of the Fourier series representation of a periodic signal as a superposition of harmonically related complex exponential signals. Now, we can write x of t as follows. A0 plus k from 1 to infinity ak e to jk omega 0 t plus k from minus 1 to minus infinity a minus k, not a minus k, but ak e to jk omega 0 t. Okay, so we have decomposed the series into these two series, and also we have written a0 separately. Now we can do the following. For this second expression here, we can let k prime be equal to minus k. So this becomes k prime from 1 to infinity a minus k prime e to minus j k prime omega 0 t. Okay? But we can also see that here k prime is only a dummy index, so we can change it to any index we wish. We can call it ml, and y we can call it k. So we can change k prime to k and write x of t in the following form. X of t is equal to a0 plus k from 1 to infinity ak e to jk omega 0 t plus a minus k e to minus j k omega 0 t. Okay, so we have expressed the Fourier series in this form. Okay, then we can do the following. We remember that e to jk omega 0 t is equal to cosine k omega 0 t plus j sine k omega 0 t, and e to minus jk omega 0 t is cosine k omega 0 t minus j sine k omega 0 t. So x of t can be written in the following form: a0 plus k from 1 to infinity. Now we can combine the coefficients of the cosine terms as ak plus a minus k. So multiplied by cosine k omega 0 t plus k from 1 to infinity, and we can combine the coefficients of the sine terms. So it is j ak minus a minus k sine k omega 0 t. Okay? So we have expressed x of t, now the periodic signal x of t, in terms of a superposition of cosine and sine signals. Okay, now let ak prime be equal to ak plus a minus k, and ak double prime be equal to j times ak minus a minus k. Okay, so x of t is equal to a0, the constant term, plus k from 1 to infinity ak prime cosine k omega 0 t plus k from 1 to infinity ak double prime sine k omega 0 t. Now this expression is called the trigonometric form of the Fourier series, because now we are expressing the Fourier series as a series expression in terms of the trigonometric functions. So this is the so-called trigonometric form or version of Fourier series. Okay, now we have obtained this new form of the Fourier series. So what can we now say about the coefficients ak prime and ak double prime? Okay, let us look at this problem. Okay, so the coefficient of the coefficients of the cosine signals in the Fourier series representation. Let us look at that first. ak prime, this is equal to ak plus a minus k. So this is equal to, now ak is equal to 1 over t0 from t0 to t0 plus capital T0, we integrate over a period, x of t e to minus jk omega 0 t integrated with respect to t. And a minus k is equal to 1 over t0. Again, the integral from t0 to t0 plus capital T0, x of t e to, now we have minus k, therefore we have j k omega 0 t integrated with respect to t. Okay, so we can combine these two expressions as follows: 1 over t0, the integral over a period from an arbitrary t0 to t0 plus capital T0, x of t, then we have e to minus jk omega 0 t plus e to jk omega 0 t integrated with respect to t. But we recognize this term here as 2 cosine k omega 0 t. Therefore, ak prime is equal to the coefficients of the cosine terms. Okay, we can take the 2 outside the integral, 2 over t0, the integral from t0 to t0 plus capital T0, x of t cosine k omega 0 t integrated with respect to t. Okay, so this is how we calculate ak prime by means of the integral of x of t times the product of x of t and cosine k omega 0 t integrated over a period. Now similarly, we can write the coefficients of the sine signals. ak double prime is equal to j times ak minus a minus k. So this is equal to, now we are going to do similar calculations. So we can write this as j over t0. Okay, j is the multiplier, j over t0 from t0 to t0 plus capital T0. Okay, we have x of t, then similarly we have e to minus jk omega 0 t minus now e to jk omega 0 t integrated with respect to t. Now we recognize this term as, now as you see, e to jk omega 0 t has a minus sign. Therefore, we have this is equal to minus 2j sine k omega 0 t. So this gives us the following expression. Let me continue over here. ak double prime is equal to, now j times j is minus 1 and we have another minus sign. So we have 2 over t0. The integration is over a period, and we integrate x of t multiplied by sine k omega 0 t. Okay. So ak and ak double prime, ak prime and ak double prime are calculated by means of these integrals. Or if ak's are given, we can calculate them directly by using the expressions we have derived. Now, if we here we have an important detail. Now, remember that in the calculation of AK prime and AK double prime, K is starting from 1. Okay? But we can extend K to 0 and consider the integral we have obtained. So for K equal to 0, AK prime becomes A0 prime, which is equal to 2 over T0, the integral from T0 to T0 plus capital T0, x of t, and cosine k omega 0 becomes 1 because k is equal to 0, integrated with respect to t. But as you see, this is nothing but 2a0. And a0 is the constant term in the Fourier series. So x of t, okay, with this convention, x of t can be written as, in terms of these primed coefficients, a0 prime over 2, which is equal to a0, plus k from 1 to infinity, ak prime cosine k omega 0 t, plus k from 1 to infinity, ak double prime sine k omega 0 t, which is the expression given in certain textbooks or in the literature in certain applications, the trigonometric form of the Fourier series as well. But now, as you see, all of the coefficients are calculated in terms of the trigonometric signals, sines and cosines. Okay, the next question is the following. Up to this point, we didn't say anything about x of t. X of t can be real valued or complex valued. So all of these discussions are valid for real valued or complex valued signals. But what happens if the signal is real valued? What can we say about the coefficients of the trigonometric form? So now let us look at this problem. Now, for real valued signals, we know that the Fourier series coefficients satisfy a certain relationship. So if x of t is real valued, then a minus k is equal to ak conjugate. So we can use this result to obtain the trigonometric form. Okay, because we know that ak prime, the coefficients of the cosine terms, is ak plus a minus k. So this is equal to ak plus ak conjugate. Remember that if you have a complex quantity, the sum of that quantity plus its conjugate is 2 times the real part of ak. And for the coefficients of the sine terms, ak double prime, we have j ak minus a minus k. So we have j times ak minus ak conjugate. But we know that ak minus ak conjugate is 2 times j imaginary part of ak. So j multiplied by j gives us minus 1. So ak double prime becomes minus 2 times imaginary part of ak. Okay, so for real valued signals, in the trigonometric form of the Fourier series, we can evaluate the coefficients by using these expressions. Okay. Now let us see an example. Okay, let us consider the following pulse p of t, which is equal to a between 0 and t0 and 0 elsewhere, and we have the periodic extension of this pulse as m from minus infinity to plus infinity, p of t minus m t0, and we choose t0 to be greater than small t0. So we have the periodic extension of the pulse, rectangular pulse p of t. So we have the rectangular pulse train. However, now let us remember the following. How can we obtain the Fourier series representation of x of t? In fact, let us consider a result we have obtained before to obtain the Fourier coefficients in a straightforward way. So we have, let us call this signal x prime of t. X prime of t is the following signal. It is the rectangular pulse from minus t0 over 2 to t0 over 2, and we have the periodic extension. At t0, we have again the pulse repeated, and similarly over there. So we know that x prime of t has the Fourier coefficients a, okay, the magnitude here is a t0 divided by capital T0 sinc K T0 over capital T0. Okay, but in our example, x of t is the periodic extension of the pulse p of t, and as you see here, the signal x prime of t therefore is related to x of t in the following way, by means of a simple translation or time shift. We see that x of t is the time shifted version of x prime of t, and the amount of time shift is t0 over 2. Okay, so x of t will have the Fourier series coefficients given by the Fourier series coefficients of x prime of t by using the time shift property a t0 divided by capital T0 sinc k T0 over capital T0 e2 minus jk omega 0 T0 over 2. So the time shift corresponds to a phase shift in the frequency domain, as we remember. Okay, so how can we now obtain the trigonometric form of the Fourier series? Of course, we can calculate the coefficients very easily by means of the this expression we have obtained as the Fourier series coefficients in the complex exponential case. So how do we evaluate the coefficients in the trigonometric form? So that will be our next concern. Okay. Okay, so x of t has the Fourier coefficients given by a t0 over capital T0 sinc k t0 over capital T0, and we have this complex exponential term e2 minus jk omega 0 t0 over 2. Okay, so we can write the Fourier coefficients as follows. Okay, so before that, now we know that x of t is real valued. Okay, x of t is real valued. So the Fourier series coefficients of the trigonometric form. Okay, let us remember the trigonometric form. So x of t is equal to a0 or a0 prime divided by 2 if you wish, plus k from 1 to infinity ak prime cosine k omega 0 t plus k from 1 to infinity ak double prime sine k omega 0 t. Now ak prime is, remember, ak plus a minus k, or in this case we have the real valued signal, therefore we have ak plus ak conjugate or 2 times real part of ak. So ak prime, now this is ak in our case, ak prime will therefore be equal to a t0 over capital T0 sinc k T0 over capital T0 cosine k omega 0 T0 over 2. Of course, we should write the term 2 at the beginning because we have 2 times real part of ak, and similarly ak double prime is equal to remember the general expression j times ak minus a minus k, or j times ak minus ak conjugate, which is j times j 2 imaginary part of ak, which means minus ak, minus 2 imaginary part of ak. So ak double prime in our case will be equal to, okay, the imaginary part of the expression is the only complex quantity is the complex exponential, and its imaginary part is minus sine k omega 0 t0 over 2, and we have another minus sign, so we have 2a t0 over capital T0 sinc k t0 over capital T0 sine k omega 0 t0 over 2. Okay, so these are the Fourier series coefficients in the trigonometric form. Now it may be a nice exercise to try to evaluate these coefficients ak prime or ak double prime by using the expressions we have derived during our discussion related to the trigonometric form of the Fourier series. For example, ak prime can be calculated as 2 over t0, the integral over a period. For example, we can integrate from 0 to t0, x of t cosine k omega 0 t integrated with respect to t. Okay, now we know that x of t is only non-zero from 0 to small t0, and there it is equal to a cosine k omega 0 t. We integrate this expression. So it is 2a over t0 sine k omega 0 t divided by k omega 0 evaluated at the integration limits. Or this is equal to 2a over t0 sine k omega 0 t0 divided by k omega 0. Okay, now if we compare this expression with the expression we have found before, they seem to be different, but in fact they are equal, and we can verify this as follows. So let us look at this expression of ak prime. So ak prime is 2a over 2a small t0 divided by capital T0. Now we can write down the expression of the sinc function explicitly. Sine k pi T0 over capital T0 divided by k pi T0 divided by T0, and we have cosine k omega 0 T0 over 2. Okay. Now we can write this expression as follows. Look at this cosine term. So it is cosine of k. Now omega 0 is 2 pi over T0, T0 over 2. Okay, so this is equal to, so these two terms will cancel out. We have cosine k pi T0 over capital T0 multiplied by sine k pi T0 over capital T0. So this is by using a trigonometric identity. This can be written as 2a, okay, T0s will cancel out as well. 2a over capital T0. It is sine of k, okay, sine of k. We have sine times cosine, so, and the arguments are equal, so we will have twice the argument. So sine k 2 pi T0 over capital T0 divided by 2 divided by k pi over T0. Now this 2 can be included in the denominator, and we can write this as 2a over T0 sine k. Again, 2 pi over T0 can be converted back to omega 0, omega 0 T0 divided by k times, now 2 is included in the denominator, 2 pi over T0, which is equal to omega 0. So we have obtained the same result, obviously. Okay, thanks for watching.